All right, let's talk about predicting the future. Now, not with a crystal ball. We're talking about a tool that's the very heart of modern data science. In this explainer, we're going to pull back the curtain on one of the most powerful and, honestly, intuitive ways to predict numbers: tree-based regression. Whether we're talking house prices or sales figures, we're about to break down exactly how this thing works and why it is an absolute game changer.
We all love simple models. We love trying to fit a nice, neat, straight line to our data. But let's be real. When does the real world ever move in a straight line? Real data is messy. It's chaotic. It zigs, it zags, it has all these complex patterns that a simple straight line it can't handle it. So what do you do when your data refuses to cooperate?
Okay, so check this out. This single image says it all. Over on the left, you see the linear model. It's like trying to measure a curvy road with a steel ruler. It just doesn't work. It misses everything. But then, look at the right. The tree-based model is like a super flexible measuring tape that follows every single curve and corner perfectly. In a complex world, you need flexibility, and that's exactly what this gives us. So here's our game plan. First, we're going to officially move beyond that straight line. Then, we'll get into the fun part, learning to think like a tree. After that, we'll peek under the hood and see how a tree actually makes its decisions. We'll weigh the pros and cons, and finally, we'll look at where these models are making a huge difference out in the real world.
Look, simple models have their place. A straight line is awesome for simple, clear relationships. But the world is rarely simple, right? We need something that can handle all the twists and turns that real data throws at us. We need a tool built for complexity.
And that's where tree-based regression steps in. The core idea here is so smart. Instead of trying to create one super complex rule for all the data at once, it just chops the problem up into smaller, bite-sized pieces. It's the classic divide and conquer approach, and trust me, it works incredibly well.
So let's get into how these things actually work. And what's so cool about decision trees is that they're not some mysterious black box. They actually think a lot like we do, making a series of simple choices to get to a conclusion. It's surprisingly intuitive.
Honestly, it all boils down to these 3 simple steps. First, the algorithm picks one feature from your data and uses it to split the group in 2. It does this by asking a really simple yes or no question. And then it just does it again and again. It just repeats this process, slicing the data into smaller and smaller groups until it's confident enough to make a prediction.
And this whole process creates a structure that looks exactly like an upside-down tree. You start at the top with the root node. That's all your data in one big pile. Each question, each split creates a decision node, and the paths between them are the branches. And when you can't split anymore, you end up at the bottom, at the leaf nodes. That's your final answer, your prediction.
Let's make this real. Imagine we're predicting house prices. We start with every single house at the root. The tree might find that the best first question to ask is the house smaller than 1,200 square feet? If the answer is yes, we go left. If it's no, we go right. For the smaller houses, maybe the next best question is, does it have less than 3 bedrooms? After a few of these questions, we end up in a leaf node, a little bucket of very similar houses. The tree's prediction? It's just the average price of all the houses in that bucket. Pretty straightforward, right?
Okay, but that brings up a really big question. How does the tree know what questions to ask? Out of all the possible features and all the possible split points, how does it pick the best one? Well, it's not random at all. It's actually a very clever and calculated process. The goal is so simple it's beautiful. At every single fork in the road, the algorithm's only mission is to find the one single split that will make its predictions better, the one that reduces the overall error by the biggest amount possible. It's always trying to make the next step easier for itself.
So how does it measure error? Well, usually it uses a metric called mean squared error, or MSE. You can just think of MSE as the tree's report card. It's how the tree scores itself. It looks at the difference between its predictions and the actual values, squares those differences, which really punishes big mistakes, and then just averages them all up.
So when you see this formula, don't think of it as just math. Think of it as the tree's playbook. This is the rule it follows for every single decision. It calculates the MSE of a group, then it tests out a split and calculates the new MSE for the 2 smaller groups. If the new combined error is lower than what it started with, hey, that was a good split. It checks every possible split and picks the one that drops the error the most. That's the secret sauce.
All right, so we know how they work. But like any tool, decision trees aren't a silver bullet. So let's get a balanced view and talk about what makes them awesome and also where you need to be a little careful.
Let's start with the superpowers, because there are a lot. First off, they are champs at handling that messy, non-linear data we talked about. They're also really tough. A few weird outliers in your data won't throw them off. They're also super low maintenance. You don't have to do a bunch of data prep like feature scaling. But you know what might be the best part? They're not a black box. You can actually look at the tree and understand exactly why it's making the decisions it's making. And on top of all that, they're like the fundamental Lego bricks for building even more powerful models.
But of course, every hero has a weakness. Their biggest kryptonite is something called overfitting. That's where the tree basically memorizes the training data, including all the noise, and then it doesn't do a great job on new data it's never seen before. They can also be a bit jumpy. Sometimes a tiny change in your data can result in a totally different tree. But here's the key, these are well-known problems, and we have some really good solutions for them.
And the main fix is a great technique called pruning. And it's exactly what it sounds like. Think of it like trimming a hedge. After the tree grows all big and bushy, we can go back and snip off the lower branches that aren't really adding much value. This makes the tree simpler, more elegant, and way better at making predictions on new data. It's the perfect cure for overfitting.
All right, so enough with the theory. Let's talk about where the rubber meets the road. Where are these models actually out there in the wild, solving really important problems for us every single day?
The short answer, pretty much everywhere. They're the magic behind real estate websites that give you an instant estimate of your home's value. They're working behind the scenes at banks, helping to model credit risk. They're in retail, forecasting sales so the right products are on the shelves. They're even in healthcare, predicting patient costs, and on factory floors, predicting when a critical machine might fail. They really are the unsung heroes of the modern data world.
So let's put it all together in a final head-to-head matchup. It really comes down to this. If your data is super simple and follows a straight line, yeah, a linear model is probably fine. But for the complex, messy, non-linear data that makes up most of the real world, the tree-based model is going to be the more powerful, more robust, and more flexible choice almost every single time.
So if you remember just one thing today, let it be this. Tree-based regression is way more than just another algorithm. It's like a Swiss Army knife for data science. It's flexible, it's powerful, and it's something you can actually wrap your head around. It's a foundational tool that really unlocks our ability to model the world in all its complex, messy, and fascinating glory.
And that leaves us with one last really cool thought to chew on. We've seen just how powerful one single tree can be. But what if one tree isn't enough? What happens when you combine the power of hundreds or even thousands of slightly different trees and have them all vote on the answer? What happens when you don't just plant a tree, but you grow a whole forest? Well, my friends, that's where things get really interesting.